In this lesson, we are going to look at a number of different scenarios or situations where centripetal force plays a key role. Here we have the famous upside down bucket of water experiment. Now, if you haven't tried this already yourself, then I recommend you do, if you can. If you can't, at the very least, watch a video of the experiment, and I've posted a link for that. So basically what you do is you tie a rope to a bucket handle and you put some water in the bucket and you gradually swing the bucket in a circle, eventually achieving a vertical circle as shown on the right. Looking at the left-hand diagram, I'm drawing a distinction between the bucket and the water inside the bucket. These are two separate bodies. They interact, but they're separate bodies. On the right-hand diagram, I'm showing you the various positions of the water in the bucket as the water describes uniform circular motion. So the water begins at the bottom of the circle, position A. It then swings round as we see it, anti-clockwise into that intermediate middle position B, then carries on up to the top of the circle, position C. At that point, of course, the bucket is upside down, and then it continues on its way down to the other intermediate position D, and finally returning to the bottom of the circle at position A again. So that's the uniform circular motion described by the water. If you look at the left-hand diagram again, uniform circular motion can only occur if there is a centripetal force. And I've shown you with that red arrow the centripetal force, which must always equal F is mv squared over r. Let's now look at the right-hand diagram and identify the forces on the water. I emphasize the forces on the water at each of these four positions. Let's begin with position A. Before I show you, try to identify the forces on the body of water. Well, there must always be weight mg. That can't be escaped. So we can add that in at each of the four positions. The weight mg will always point vertically downwards. It never changes direction, and it will always have the same magnitude, mg. So there, in all four of my positions for the water, I've shown the weight mg. Now, what other force is acting on the water? Well, it can't just be W's mg. If it were just W's mg, then the water would simply accelerate downwards under gravity at 9.8 meters per second. So there must be another force on the water. Well, let's begin at position A again. Well, in fact, there is a force acting up the way caused by the tension in the string, and it's really pulling the bucket up onto the water, so to speak. I'm going to label it tension T here because that's the original cause of this force, but it's the tension T pulling on the handle which pulls on the bucket, which actually pushes the base of the bucket up onto the water. That tension force is pulling on the bucket and therefore on the water at all positions, and you can see at position B, that's where that tension force is pulling the water. And in position C, the water's upside down now, of course. The tension force is pulling as shown. The tension force, of course, is always pulling in towards the center of the circle. It always points towards the center of the described circle. So whilst the weight's direction is constant, the tension direction changes, as shown. So there we are. At each of those positions, we have a combination of forces acting. Let's just look at that briefly at each of the four positions. Well, in each of those positions, it's the combination of the weight force and the tension force which combine to produce mv squared over r. So down at position A, the tension is opposing the weight. When you add those two together as vectors, the result is F equals mv squared over r. So the tension force is going to have to be quite big there because it's going to have to overcome the weight and also provide a sufficiently unbalanced centrally directed force to give you your desired mv squared over r. At position B, the tension is not opposed by the weight at all because the weight acts at right angles. So the tension in itself provides the mv squared over r force. Now, if that body of water is moving around with uniform circular motion, then the centripetal force mv squared over r must remain constant. So the resultant of the tension and the weight must always give you a constant F is mv squared over r. So the resultant at position A is mv squared over r, and the resultant at position B is also mv squared over r. But at position B, the tension provides the whole of the mv squared over r force, whereas in position A, the tension has to balance the weight first, and then on top of that, provide the mv squared over r force. So the tension is going to be quite big at the bottom, but smaller at position B. Now, given that we've sorted out position B, let's swing over to position D because it's a mirror image. It's exactly the same scenario except the tension's pointing to the right towards the center of the circle. But again, the weight is not opposing the tension in any way there, so the tension T provides the entire mv squared over r force itself. The interesting position is C. If you look at C, the weight is pointing down, but so is the tension. And that means that those are going to add together the weight plus the tension to provide your mv squared over r. So you're going to need much less tension up at the top than you do at the bottom or indeed at the sides. So the position of maximum tension will always be position A, the very bottom of the circle, and the position of minimum tension will always be position C up at the top. So as you were doing the swing, I wonder if you felt that the bucket felt heaviest at the bottom of the circle, that's position A, but it felt sort of lightest at position C. And that corresponds to your having to provide a large tension at position A, but a much smaller tension or pull on the bucket at position C. Right, so our next scenario is another very popular one, often comes up in exams as well. And this is the car rounding a corner on a flat road. So if you have a look at the diagram, car is driving along a straight road, but it then comes to a bend in the road, a curve. And as it rounds the curve, we're going to assume, for the purposes of our analysis, that the curve is circular. So we've shown in the diagram an approximate circle that the car is describing. It's only going around a small section of the circle, of course, to get round the bend. But if we were to draw the whole circle, you can see that it would look something like that. It's not really to scale, but that's okay. And you can see the center of the circle is shown by the dotted lines crossing. So let's imagine then the car has a mass of 800 kilograms and it's traveling into the bend at 20 meters per second. And let's imagine it maintains that speed of 20 meters per second all the way around the circular path. Let's imagine that the radius of the described circle is 100 meters and that the motion is uniform circular motion, so the angular velocity would be regarded as constant. Again, pause the video before seeing the solutions. Question 1, what force causes this circular motion? Now, before you answer that, we know it's a centripetal force, but the question is, what's causing the centripetal force? Well, it is a centrally directed force, a centripetal force, and it's caused in this case by the road on the tyres causing friction. Now in these scenarios, once you've established that a body is describing uniform circular motion, you're immediately on the hunt for what's causing the centripetal force, and it completely depends on the scenario. The only thing in contact with the car here is the road, and it's in direct contact with the tires. So they must be providing this centripetal force. So here's the same scenario, but this time you can see that we've shown the frictional forces acting on two of the tires, pointing centrally in towards the center of the circle. These frictional forces would act on all four tires, of course, and would combine to produce one overall frictional force. In the top right diagram, we've shown that frictional force, F subscript F small r for friction. That is unbalanced. There is no rightward force opposing that frictional force. So that frictional force then is going to be our centrally directed or centripetal force. The upper right diagram also shows the weight mg balanced by the normal reaction force. We often call it R. In this diagram it's called Fn for normal force. So question 2 is then find the size of this frictional force. Pause and solve. Well, the frictional force is the cause of the circular motion. It causes mv squared over r. So we can set up mv squared over r equals F of friction. Rearrange, put in our numbers, and we get that our frictional force, our centripetal force as it is here, is 800 times 20 squared over 100, giving us a final answer of 3,200 newtons of friction. That is our centripetal force. We now come to a slightly more complex problem, and this is that of a car going round a corner on a banked track. A banked track is rather like the track that you'll have seen cycling competitions on in the velodrome, where the surface of the track is at an angle to the horizontal. And if you look at the diagram, you can see the car approaching the corner of a banked track. The angle of slope of the track is theta. We're assuming uniform circular motion is being described by the car, so the radius of curvature of the track, which we assume obviously to be circular, is r, and that red dotted line is the imaginary circle described. So the car is the same as before, 800 kilograms. It's coming in to the bend at 20 meters per second, and the radius of the track is still 100 meters, but this time it's banked. So our question is, what force causes the circular motion here? I would pause now and take your pen and paper, because this one's a bit more complex, and see what you can come up with. Well, the car's describing uniform circular motion, therefore there must be a centripetal force. That's the first observation. So let's find it. You might want to pause again and see if you can come up with the detail of the forces. Well, the track reacts to the car pressing down on it by exerting a reaction force R back upwards, perpendicular to the track and to the car as shown. That's a normal reaction force, R. But if you look at R, R is at an angle to the horizontal, it's at an angle to the vertical. So we can resolve R into two perpendicular components, a horizontal one and a vertical one. Pause again if you haven't already found these. So Rx and Ry are our components. If you look at the diagram now, there's Rx. It's pointing horizontally. Notice it's pointing in towards the center of the described circle. That's going to be important. Ry points vertically up the way. It does not contribute to the the centripetal force in any way because it's not pointing towards the centre of the circle. So it's Rx that is the centripetal force, in which case we can say that Rx, that horizontal component of the normal reaction force, is mv squared over r. Okay, to finish off this lesson, we're now going to analyse these forces in a little bit more detail, and then we're finished. So, the last part of this lesson has our looking in detail at the force diagram, the free body diagram of the car on the banked track. Now, if you ever have to draw one of these, just draw the view from the sort of rear as the car is going into the page, so to speak. And there you can see the bank track looks like a triangle in section with angle theta. It's easy just to draw the car as a circle, just sitting bang on the track, just keeps the diagram simpler. So let me take you through this diagram. Well, first of all, we have the two main forces are the weight mg pointing vertically downwards, making a right angle with the ground, and the normal reaction force R, it's perpendicular to the track itself. So those are the two main forces. The green and purple forces are components of R, so be careful about components. These are not separate forces, these are part of R, essentially unpacked. So the geometry of the situation, I hope you can see that the angle between the centripetal force and the slope must also be theta. You can see that from our kind of Z-shaped angles. If I call the angle alpha that's shown there, then hopefully you can see that alpha plus the theta equals a right angle, and that means that the angle between the green and the red vectors is also theta. You might want to take some time just to convince yourself that those two angles are indeed theta. Well, it follows that Rx, the horizontal component of R, is R sine theta, and that the vertically upwards pointing component of R, Ry, is R cos theta. Pause the video for a moment and just sketch that diagram and convince yourself that the forces are as shown with those angles. Okay, so we've resolved the normal component R into R cos theta, the y component of R, and R sine theta, the x component of R. Looking at that diagram then, R cos theta balances the weight. The car is neither moving up nor down. So R cos theta equals mg, that's balanced. But R sine theta is not balanced by a rightward force at all. And R sine theta then is the unbalanced force causing the centripetal acceleration. So the car is describing uniform circular motion. So there must be an mv squared over R force coming from somewhere. I think we've now concluded that in this particular case of the car rounding a corner on a banked track, the centripetal force mv squared over R is given by R sine theta. Let's call that equation 1. I think we're also now clear, I hope, that the weight's balanced by R cos theta, so that's equation 2, mg equals R cos theta. We're now going to divide equation 1 by equation 2. Now it's not obvious why we're doing that until we've done it, so this is just one of these little techniques that is commonly used in these problems, and you really just have to get used to it. But when you're doing these problems, you almost always set up those two equations and then divide one by the other. Why? Well, let's have a look and see. If we divide one by the other, the two left-hand sides give us mv squared over R divided by mg. That's our new left-hand side. And on the right-hand side, we get R sine theta over R cos theta. See if you can spot why that is a useful thing to do. Well, on the left-hand side, what's going to cancel? M. And on the right-hand side, something's going to cancel. That's R. And you should know that sine divided by cos gives us tan. So we end up with a simplified expression, v squared over r, and taking the g across to the right, equals g tan theta. Rearranging that one more time, we get v squared equals gr tan theta. So that's the equation which gives us the velocity that must be attained by a car to experience uniform circular motion when it's going around a bank track, radius r, angle theta. Look at that equation. Notice that if the car goes faster, i.e. v increases, then theta must increase to allow the cornering. So if we imagine a track with a fixed radius, fixed curvature, if the car goes much faster, then theta must increase. That means there's an upper maximum speed a car can go at on these bank tracks. If it goes any faster, it will be unable to take the corner, and of course it could crash. So the faster the car goes, the steeper the bank angle of the track must be.